estuaries. For example, the clam resources of 6 of Oregon's estuaries, where significant recreational clamming occurs, have been well documented by ODFW's Sea Corps program. The example here is for 4 species of clam surveyed at Bridge Flat, Yaquina in 2012. These surveys are also available for clam populations in Tillamook, Netarts, Siletz, Yaquina, Alsea, and Coos Bay. Commercial clamming also occurs in Oregon's estuaries, but only in Tillamook Bay is there a significant commercial harvest of bay clams, as you can see from this graph. Several species of crabs suitable for sea otter consumption occur in Oregon's estuaries, and recreational crabbing for Dungeness crab occurs in all bays where species is present. 4 of Oregon's estuaries support commercial oyster farms. There's very little published information about whether sea otters consume oysters. Based on anecdotal reports, in areas where sea otters and commercial oyster operations overlap in Alaska, there have been minimal interactions. However, unlike the Oregon fishery, where the majority of oysters are grown directly on the estuarine bottom, as seen here, the Alaska operation utilizes hanging bags or enclosures that may discourage sea otter interactions. My task was to see if the habitat characteristics of Oregon's coastal ocean was still suitable for sea otter survival. Looking at what we know about Oregon's estuaries, here is a summary of characteristics for 8 estuaries that is relevant for their assessment as a potential site for sea otter reintroduction. The size of the estuary and the presence of eelgrass communities gives an indication of the availability for foraging and for resting habitat for otters. The existence of commercial or recreational harvest activities can be viewed as a positive indicator of the potential prey availability. However, these fisheries and the presence of oyster farming and shipping activities also represent a potential for human-otter conflicts in the case of sea otter recolonization. This summary suggests that 3 larger estuaries, Tillamook, Yaquina, and Coos, have an optimal combination of prey resources. They have clams, crabs, and resting habitats, the eelgrass beds, tidal creeks, suggesting they could potentially support viable sea otter populations. Yaquina and Coos Bay have the additional advantage of proximity to outer coast reefs and kelp beds that could provide alternative habitats for establishing sea otter populations. Likewise, in terms of outer coastal habitats, the data indicates there are several areas of the coast that could be potential sites for sea otter reintroduction that have relevant habitat features and prey populations. These occur primarily in the southern half of the state, where rock habitat and kelp beds are more common. They include the Depot Bay, Yaquina Head region, Cape Arago, south of Coos Bay, and the reef complexes near and to the south of Port Orford and Gold Beach.
All right.
All right. I'll tell Jan thank you next time I see her.
Perfect.
Yeah, good. That was excellent. Yeah, check out the chapters in the feasibility study on the habitats on the Oregon coast. There's just an intense amount of information gathered from a wide variety of sources, maps, charts, the whole 9 yards. So it's a rich document for that. We've got a couple minutes before Dr. Tim, but let's get started anyway. You think, Chanel?
Yeah, I'm gonna have one little plug here for our prizes for participants on our symposium for day 3. We've got another Jacobson salt sea otter tin up for grabs. They are completely sold out, so very limited edition. Delicious sea salt made from Netarts Bay.
Collector's item.
Yes, it is. And then we have super special from Salty Textiles, who dyed this yarn with urchins that she harvested in California to help control their population. And volunteer knitted by Haley Stitch Witchery, which you can find on Etsy. So we have a beautiful knit hat and also a urchin dyed shawl as well.
Ooh, Gibbs.
This is pretty cool. I want it really bad, but we are going to give it away to you, someone who is participating today and following along with us. Thank you so much. And also thank you to everyone who's using the Q&A feature to ask questions of our speakers today. And with that, Tim, if you're ready, we'd love to have you go.
I'm going to say a few words about Tim. I, of course, came across Tim's name in the literature as I got underway here with this Elakha Alliance business and was looking at for background science articles in understanding sea otters and their habitats and so on. And Tim's name frequently popped up. But it wasn't until Dominique Kone was a graduate student at Oregon State. Many of you know Dominique. He did his master's on a potential recovery or restoration of sea otters to the Oregon coast. And Tim was on his thesis committee along with Steve Rumrill and of ODFW and Lee Torres, OSU. And that's when I met Tim. And right off the bat, just the depth and width of this guy's knowledge and connections into the sea otter science community convinced me that he was the right person to lead a feasibility study for us. And so I twisted his arm. He agreed over Chinese food one day to do it. And I think he ultimately decided it was against his better interest, but I think he's having fun with it ultimately. We also then convened a team of, and he'll tell the story, but a team of the additional scientists, Jim Estes, Sean Larson, Jan Hodder, Jim Bodkin, and Mike Murray, to join him as contributing authors for this study. But really the piece de resistance of this entire effort in some ways is the sea otter population model that is a cutting edge tool for trying to predict where and how many sea otters there might be in various areas of the coast based on a whole suite of complicated criteria. And together, this population model has already allowed us to do a little peek into the future of what it might look like to bring sea otters back to Oregon. So with that introduction, I'm hoping that you will enjoy this population model exercise as much as I have and learn from it. And so I'm going to turn it over to Tim and let him take the rest of the afternoon. After which you will bombard him with questions. There will likely be questions for Sean as well. And the ones for Jan, we can forward to her. But with that, I want to thank everybody for attending this feasibility study symposium. And Dr. Tim, it's all yours.
Thank you very much, Bob. And I will say in advance that out of the blue, I've suddenly started having internet issues about half an hour ago. So I'm hoping I'm not going to cut out at any point, but if I do, I will try and reconnect as fast as I can. So I'm going to try and share screen now. Oh, okay. So
we can see it.
You can see it. Okay, good.
Victory.
So far, so good. We'll see what happens. Right. So, well, thank you for that introduction, Bob, and thank you to Sean and Jan for those earlier presentations that really helped set things up for this one. I'm going to try to do what might seem impossible, which is try to make population modeling seem fun and joyful. I may or may not succeed, but I will do my best and hopefully provide some insights into what we have learned about the potential for population growth and recovery of a reintroduced population in Oregon using population modeling tools. So let's see if I can make this go forward. So what do we mean by a model? Different people have different ideas of what models are, and I'm not talking about this kind of model. In ecology, a model is an abstract mathematical representation of an ecological system, and it is used and studied to better understand the actual system that the model is representing, which brings to the surface the most important thing to remember about models. Is they are not reality. They're not even meant to be reality. They're an abstract caricature of a reality, but that nonetheless may be useful sometimes. So population models relate individual level responses, things like vital rates, births, deaths, and also behavior, to changes in population density and structure. In essence, a model is simply a mathematical tool that can help us understand complex systems and support decision-making. So that's what we're referring to in the sense of a model here. So why do we need a population model for Oregon, or for that matter, for anywhere else that sea otters occur? Well, there are, in the case of a reintroduction to Oregon, there are many questions and uncertainties about what might happen. Some of these questions include things like, can a reintroduction to Oregon succeed? How many otters would need to be reintroduced to ensure a successful reintroduction? And where should those otters go? And then sort of more detailed follow-up questions. What should be the age and sex composition of a reintroduced population? Should it be mostly younger animals or mostly older animals, mostly females, or an even split between males and females? What reintroduction strategy might be the most successful? Jim Bodkin touched on some of these strategies that have been used in the past in different areas in his talk a couple of nights ago. I'll cover a few of these as we move along, but suffice to say, as well as those earlier questions of how many and where, there are different ways that those animals can be introduced to the environment in Oregon. And so the models can be used to evaluate those different strategies. And finally, given that a reintroduction did occur, what are the likely scenarios of future population growth and distribution as we move ahead in time? Those projections of future growth and distribution over time can be really useful and important for calculating what the ecological effects of sea otters might be as they recolonize habitats in Oregon, and what the socioeconomic impacts of reintroduced and growing sea otter population could be, as Jan just alluded to in her talk. So that brings us to the models. And can a model predict the future? Given a particular reintroduction scenario, can the model tell us how many otters will occur in the population each year in the future, and where they will be, and the density of otters everywhere along the coast each year going into the future? And for that matter, whether the reintroduced population will succeed with certainty. As you might guess from this picture, a model is not an oracle. So the answer to all those questions is no. A model cannot predict the future, and it cannot answer all those questions with certainty. So then, which brings us back, why a model in the first place? What can a model do? Well, what the model can do in this case is to synthesize all the existing knowledge and information we have about sea otter population biology, behavior, spatial ecology, and the outcomes of past reintroductions. And we can use a model to you can use it in a way that is demographically coherent and transparent. And what I mean by transparent is we can list all of the assumptions and make clear exactly where these projections come from. And if someone disagrees with the model, they can review the code, they can look at the equations, and they can come up with a better way. And if there is a better way, then we'll switch to that. So it's not a black box, it's an open box, thus the transparent idea. So we can use these methods to come up with demographically coherent methods to probabilistically project a range of outcomes. So that term probability, as you probably know, scientists use that term a lot. It just simply means we can never predict the future with certainty. We can speak probabilistically about what might happen in the future. Some outcomes are very unlikely, and other outcomes might be more likely. And so that's what a model can do. It can tell us about those likely outcomes under different scenarios. And that information can help us make informed decisions about some of the key questions and variables that I mentioned before: how many, where, what age and sex, and best release strategy. And finally, the model projections can give us estimates of future abundance and distribution, but not with certainty, but rather with associated uncertainty measures, again, probabilities. And I'm going to be showing you some graphs that will make sense of what I mean by associated uncertainty measures. So in the case of sea otters, we luckily have a wealth of past information, and that's because they have been a very well-studied species. Sean's talk sort of alluded to that. All those samples she had from around the range of sea otters have come from studies that we've done really everywhere that sea otters occur, from Bering Island in Russia to all through the Aleutian Islands, the Alaska Peninsula, down Southeast Alaska, British Columbia, Washington, and of course in California as well. A huge sort of community of researchers and conservation workers.
Oops, Tim, I'm afraid we've got Houston, we have a problem here. We've lost your audio here for a bit. We'll wait and see if we can get Dr. Tim back on the line. Living out near Halifax, Nova Scotia, it's a long way around the world. So we may have to resort to that theme music, Chanel.
Okay.
Or something.
Yeah.
Okay, he's going to sign back on here, I'm sure. Thanks everybody for hanging in there on this. This is one of the perils of these kinds of operations, but the benefits are pretty good that we can all be here and see this kind of thing when everything works right. So I'm sure Tim will get this back here in a minute. Okay, looks like he's rejoining. All right, Tim, we see your image there.
That's me.
Yeah, so that was the dreaded thing I thought might happen. I'm not sure our internet is usually pretty good here, but starting, as I say, about an hour ago, it started dropping off randomly periodically, which it just did. So well, hopefully it'll humor us for the rest of the talk, if maybe. I'm trying to share my screen.
Yep, go for it.
Okay, there's a graph. There's some of the data. Where's there we go. Okay.
There we are.
Whoa, okay. So is this about where I left off?
It is.
Mm-hmm.
Very good. Thank you, sir.
Okay, well, so yes, based on those data sets, models have been developed and are currently in use for those different populations. And so we decided to use those various aspects of those models to build something specific for the Oregon reintroduction case. So what are some of the key elements of sea otter models that we needed to ensure that we included in the Oregon population model? So first of all, importantly, survival rates differ by age and sex. Pardon me. Obviously, birth rate, reproduction varies by age and sex as well. Only adult females actually have pups, so that's important. But just as important is the fact that that animals of different age, males versus females, have different survival rates, and so the composition of the population is very important because it affects the potential growth rate of that population because of those survival rates. Survival rates also differ as a function of population status or density, particularly for pups and juveniles. This is frequently referred to as density dependence. That is the fact that as population increases in density, survival rates tend to drop. This is primarily the result of depletion of preferred prey resources. And so that continues to happen. And eventually, as survival rates drop enough, the population reaches an equilibrium, which we commonly refer to as carrying capacity. And here's a picture of a graph of exactly that phenomenon. So you can imagine the population starting out here at the lower left, and then increasing over time, but the rate of increase decreases as the density increases. That's because while birth rates are remaining approximately constant as they do in sea otter populations, death rates are increasing. And eventually, when births and deaths cancel each other out, the population stabilizes at this sort of dynamic equilibrium, a dynamic in the sense that it tends to go up some years, down some years, but overall it's going to hover around this phenomenon we call carrying capacity, or K. Another key element is that this equilibrium density, carrying capacity, is not a constant thing. It can vary over time, and very importantly, it varies over space. And it varies over space at quite small scales because it depends on habitat quality. And when I say, and Jan just told us a lot about the phenomenon, the different aspects of the habitat that determine its quality for sea otter populations. And most of them relate to the prey availability or prey productivity, actually, that determine how many otters can be supported in a given area. So the map you see here is of Southern California or the Santa Barbara Channel. And this is showing estimated carrying capacity. So warmer red colors are higher density at carrying capacity, and cooler dark green colors are lower density at carrying capacity. And you can see that there's variation at pretty fine scale. So the projections of that model for the Channel Islands show higher densities, for instance, along the south side of the Channel Islands than along the north side. So that's an important thing to include in the model. Another important element is that mature sea otters, particularly reproductive females, have very small home ranges. So that means the population dynamics also can vary at very small scales, because the conditions experienced by females in one area can be very different than those experienced by females in another area, even only 30 or 40 kilometers away. And those adult females in those two different areas are completely independent and are experiencing different resource conditions and environmental conditions. And again, that's because of this very small home range behavior. And as this map of California that you see here is just, you don't worry about too much about what it's showing. Suffice to say that the different colors are showing different rates of growth. And you can see that the rate of growth of the population at any one time is quite different in different areas of the range. And that variation happens at pretty small scales. That really high site fidelity of adult females also contributes to the very slow rate of range expansion that is seen in populations of sea otters. So only 2 to 5 kilometers per year of sort of spread of a population along the coastline. So that's another important element to include in the model. And then another key element to include in the model is specific to a reintroduced population. And that is the fact that mortality and dispersal have been found to be elevated during the first decade or so after a reintroduction. Jim Bodkin talked quite a lot about this in his talk a few nights ago. This is a map of California again here on the right, and down at the lower end here you can see San Nicolas Island, and that was the site of a reintroduction in the late 1980s. So here's a picture of the island. Otters were brought out there starting around 1987. And here is a graph, and Jim showed this the other night too, of what happened with the population. A total of 125 otters were brought out there. But as you can see, shortly after the reintroduction, or for the first 5 or 6 years or so, population effectively plummeted. And that's because of a combination of elevated mortality, but also mostly dispersal of animals away from San Nicolas Island, in some cases to other places in Southern California, and then for a lot of adults back to their original home ranges in Central California. You can see that though, after this period establishment phase, about 10 to 15 years, population growth, the population stabilizes at a low abundance and then finally begins to grow, and then eventually begins to grow quite rapidly. This is sort of the exponential growth phase. So this is the most detailed data we have from any reintroductions. Many of the other reintroductions in Washington, British Columbia, and Alaska, those populations were not studied carefully or as carefully in the first few years. So we don't quite know as much, but we believe that this sort of establishment phase is a fairly typical phenomenon of reintroduced populations, and so important to include in the model. So that brings us to the Oregon population model. We've tried to design it to capture all of the elements that I've just described. It's a matrix-based projection model that tracks abundance of juvenile and adult age classes of male and female sea otters. So there's 4 different classes. The vital rate parameters for the model are based on published studies from many other areas, although we've biased it somewhat to include vital rates from reintroduced populations, including variation and those survival rates for that establishment phase. These vital rates also include density dependence and stochasticity, meaning they vary randomly from year to year and over space. The model is spatially explicit, and what I mean by that is it's not assumed to be homogeneous population. Rather, we're modeling growth and movements between 42 population segments. And those 42 population segments are defined by differing habitat qualities, and that would mean they also have differing levels of expected equilibrium abundance or density. And so here is a map of, you've seen this in some of the previous talks, of southern, central, and northern Oregon coastline. And that you can see that these coastal population segments, there's 42 of them in total, including the estuaries. And you see the estuaries are marked up here. They have an E in their code. And you can see that there's also different colors along of the habitat along the coast. And a shout out again to Dominique Cohn, who is responsible for those different colors. Those different colors represent differing expected or potential carrying capacity based on habitat characteristics. This was the result of Dom's graduate work. He did his master's with Leah Torres at Oregon State University, and he took a model that we had developed based on habitat-based carrying capacity for California, and he adapted it for Oregon using the same types of habitat layers for Oregon that we had used for California, but local, obviously, to Oregon. And he applied all the various modeling components and equations to come up with the expected potential carrying capacity at that 100-meter grid for the entire coast of Oregon. So that's why you can see the variation in those colors at fine scale. So we've incorporated that varying carrying capacity into the population model. So the other thing we did with the model is taking it from being a bunch of very boring looking code to put it into something a little bit more interesting to look at, which is this web-based tool, the Oregon Sea Otter Population Web Tool, or ORSO. There's a link to this, or several links to this, I believe, on the Elakha website. So you can go and explore this model and play with it and have some fun with it, doing simulated reintroductions of sea otters to different areas of Oregon to see how those play out. As you can see, you see that the map there, which shows you the distribution of all the segments, and you can select segments, one or more segments that you might like to simulate reintroducing sea otters to. You can vary the number of otters or the number of otters per year in supplemental introductions. You can see all these sliders here on the left, and then a whole bunch of other parameters that you can vary: a number of years to run the simulation, the number of times to iterate the population simulation, and a bunch of other things that are going to affect how, well, among other things, how long it takes to run the simulations. And then you can get output from those simulations, which we're going to be looking at a whole bunch of in just a second here. So this is the interface. Underneath that interface is all the sort of elements that I've just described to you in the previous slides, boiled down into a bunch of equations that describe survival and growth and reproduction, and demographic transitions, all of which lead to the projected changes in abundance and distribution over time. So here's what some of the model output looks like. There's 2 primary types of output, one of which is a map that shows you the expected distribution of otters at the end of the simulation period that you've specified. So if you say you want to look at 25 years of growth, it's going to show you what the expected distribution of otters looks like after 25 years. And you can see it's sort of a heat map. It's color coded based on density. In general, you'll see the highest density in the close to the area where you release the otters, although you'll see that it also sort of diffuses over space, showing you the results of the population spread over time. And then the other thing it will output is a graph of projected expected trends in abundance over time, given sort of the scenario that you're looking at. But you'll see there's sort of this gray band of uncertainty around the projections. So these 25-year model projections we're going to be looking at over the next few slides. And again, these gray bands show you the 90% credible interval for what you would expect the population to do. And that's still only 90%. That means that 10% possibility that it'll grow even faster or will grow even slower, potentially going to extinction as well. So this is the band of potential growth over time that we feel about 90% certain the population will be within in that scenario. So again, that's that uncertainty that we were talking about before. So I'm going to show you some projected outputs of scenarios for 4 scenarios of interest. And these involve potential releases to these 4 different areas of the coast, which include both outer coast habitat for scenarios 1 and 2, and then a mixture of coastal and estuarine habitats for scenarios 3 and 4. And in all of those scenarios, we designed them to try to attempt to have on average 200 otters after 25 years on average. Obviously, some scenarios will be simulations higher, some lower. So we adjusted the number of otters that you would have to introduce at the beginning to achieve that mean of 200 after 25 years. So here's what those scenarios look like. So scenario 1 for rogue reef, you can see this actually, the graphs I'm going to show you here, a slight correction, I'm going to show you graphs where we released 100 otters in all of these scenarios, and differing things happen. I'll show you the other simulation in just a minute where we targeted it for 200. So these are showing what happens if we release 100 otters for each of these scenarios. And as you can see, there's that establishment phase where we expect the population to decrease as animals disperse and die, but then eventually becoming established and increasing. Similar thing for scenario 2 at Port Orford. And again, you can see the expected distribution on the left. Scenario 3, Coos Bay and Cape Arago. And I apologize for my pronunciations of any geographic names. And finally, scenario 4, Yaquina Bay and Otter Rock, outer coast area. So you can see fairly similar patterns for all those, although there are subtle differences in the expected patterns of growth and the relative uncertainty around those. As a general trend for all of these, we can see that the probability of success increases with the number of otters introduced. So introducing anything less than about 60 otters gives us a significant probability that the population will go to extinction. And that is shown by the gray uncertainty band intersecting 0. So we can't say with 90% probability that a introduced population of less than 60 is not going to go to extinction. Once you start to get above 60, then you start to be relatively confident that it will succeed. Although again, I point out this is only the 90% band, so there is still some possibility that any number of animals introduced is not going to succeed. And here's that other, what I thought I was going to be showing you. This is just showing you the number of otters needed to achieve that average target of 200 otters in 25 years by the different scenario. So you can see that there's different numbers of initial otters needed at the different locations. The fewest number of otters to achieve the target of 200 would be the Port Orford, Cape Blanco scenario. And this is just showing you a comparison of expected performance for 100 otters released at any one of the possible coastal segments, and after 25 years. And as you can see, there's quite a bit of variation with that peak around the Port Orford area. That's the highest value right there, that the most likely to achieve the highest number of otters after 25 years. Other areas are quite low, and then other areas are in between. So this sort of can be used as a way of looking for sort of sweet spots. This area here seems to be an area that is has fairly high likelihood of success, higher numbers of otters expected after 25 years. Oops, wrong way. And then there's the issue of release strategies. Up to now, I've been showing you scenarios where have a single release site, and we're releasing one group of otters to that site. But there are other possible things that could be considered. One of those, for instance, is having multiple release sites. This was used very successfully in Southeast Alaska, or I guess the definition of success depends on your perspective, but it resulted in probably the reason that the Southeast Alaska reintroduction has resulted in the highest population growth of any of the reintroductions, with over 25,000 otters as of the last population estimate, from originating from just a little over 450 animals released in the late 1960s, early 1970s. The reason that growth is so astonishing is that it wasn't really a single reintroduction. It was actually 7 different reintroduction sites. So the multiple, because of that high site fidelity I mentioned before of adult female otters, when you have different reintroduction sites that are sufficiently geographically dispersed, they essentially form initially distinct populations, each doing their own thing and growing exponentially and spreading along the coast at their individual sites. And this leads to more than a doubling of what you would expect if there was just the same number of animals released to a single site. And this just shows that right here. So after 25 years, if you translocated 100 otters to section 6, the mean expected number of otters after 25 years is 69. But if you translocated only 70 otters to 2 different sections, after 25 years, the total expected number is 126. And these, be aware that the y-axes are different on these 2 graphs. That's my bad. But that's why, so this graph on the right is actually showing considerably higher, about doubling of population growth, even though there are fewer otters initially introduced at 2 different sections. Another set of considerations, which I'm not showing here, is that the issue of estuarine release sites versus outer coast release sites. That was something we looked at and can be looked at as well with the population model. One of the things that we believe, based on the Elkhorn Slough experience, is that an estuarine release site is more amenable to recapturing and helping out otters that are distressed, and therefore leading to potentially a higher survival rate and overall success rate for a group of reintroduced otters in an estuary, because it is this enclosed area. So even a smaller number of animals in an estuary might have a higher probability of successfully taking and then eventually emigrating out of the estuary to the outer coast nearby. So that's another thing that can be looked at with the model. So in summary, the results of the simulation model can be used to help guide selection of optimal reintroduction sites, strategies, and the strategies include numbers of animals and different age and sex composition of the reintroduced population. And they can also help inform the assessment of potential ecological and economic impacts by projecting what the expected density and distribution of a reintroduced otter population will look like over the subsequent decades. And that's in fact what we're working on right now, or is being worked on right now with the economic impacts assessment, is to take those projections and translate them into some of the socio and economic impacts. So with that, I think that's all I have to say today, but I'd be happy to take questions because I know I left a lot of things out, and I hope that there's still some people watching because I don't know what my internet's doing.